Good evening, everyone. I hope you are all doing well and staying safe. Here is Mariam Shref, a petroleum engineer from Lebanon, and I would like to welcome you all to our second lecture of the series of lectures titled Introduction to Cased Hole Logging, presented by a distinguished guest speaker, Dr. Moustafa Oraby. Dr. Oraby is currently a petroleum engineering professor and the director of the graduate program at the American University in Cairo. He has over 25 years of experience in the petroleum industry, where he worked for both operating companies such as Arco Exploration and Production Technology and service companies such as Halliburton and Schlumberger. He has a global experience where he worked and lived in North America, South America, Europe, Middle East, and Far East. Dr. Arabi's research interest areas are low salinity enhanced oil recovery, seismic enhanced oil recovery, and unconventional reservoir evaluation and stimulation. So please join me in welcoming Dr. Oraby. So welcome, Doctor, and we are pleased to have you with us today. And as a final reminder, if you have any question related to the technical content of the presentation, please feel free to drop it down in the Q&A section. Now, without any further ado, Dr. Oraby, the mic is yours.
Thank you, Mariam, and welcome everybody to the second lecture on the introduction to cased hole logging. In the previous lecture, actually, we covered the inside the wellbore. So we talked about how to evaluate or identify zones that can produce gas, zones that can produce water, also how to calculate and define the flow rates, measure the velocity of the fluids inside the wellbore. So to continue on what we started, let me remind you of our definitions of what is cased hole logging. And we said the cased hole logging looks at three different parts of our reservoirs or our field in a way. Inside the wellbore, between the wellbore and the formation, and outside the wellbore. Okay, and we said that inside the wellbore is mainly fluids. Between the wellbore and the formation is the casing and the cement, and then inside our formation is the formation fluid. Then we started saying that what we really concerned about inside the wellbore is the types of the fluids, velocities, the flow rate. Then between the wellbore and the formation, we talk about the condition of the cement and the casing. Then outside the wellbore, which is our reservoir, is the fluid saturation, because the fluid saturation changes. We produce fluids, then things start to change, and we have to monitor the changes on periodical time. Sometimes we do it every 6 months, sometimes we do it every year. It depends on how the company plans to monitor the changes of that in the reservoir. So in this case, or today, we'll start talk about the other two. So expect that the lecture will be a little bit longer. I hope that can we cover it in an hour or an hour and a half, so we can actually get some information on what is it, the casing, the situation of the cement and the casing, and also how we calculate the saturation behind pipes. Okay? So to start with the cement operation, let's assume this is our wellbore, and then we started descending the casing. So here is our casing. Between the casing and the wellbore wall, this zone, we call it the annulus. So the annulus is a spacing between the casing and the wellbore. Then we start cementing all this annulus with the cement. So we pump the cement from above, and the cement will start getting through the annulus and gets up into the between the annulus and the between the formation and the casing and the annulus, and try to fill the gap between these two. Now, the condition is, did we really fill this gap properly? Do we really have cement between the casing and the cement itself? Do we have any bonding between the cement and the formation? So the bonding between the cement and both the casing and the formation is our concern. We don't like to see any gaps between the cement and the casing, or any gaps between the cement and the formation. That's in our industry, we call it integrity. The well integrity is really very important, because it can be a disaster if the casing is not in a good shape. Okay, so everybody, we always monitor the status and the condition of our wellbore, especially for the cement. Okay? So what are the possible cement problems? We need to first, before we look at how we measure it, what are these problems and how can we measure and overcome? Now, if there is our formation, and then we put the casing in here, and our goal and aim is to fill the spacing between the casing and the formation with the cement. Okay, so one of the most important part is look at the bonding, how the cement and the casing are bonded, and how the cement and the formation are bonded. So this zone is very important. We need to make sure there is really a cement and casing contact here. The bonding exists. Also, we need to look at that zone. Also, we need to look at between. Is there any voids here in the cement? So all of these, if they are not in a very good shape, that can put the well in a really danger. Can lead to blowout. Can lead to failure. So many problems that we don't want to have it, because the cement and is a very important or essential part in our well design. So if you look at if we need to summarize, we can actually say there are multiple of them. If this is my formation, this is my borehole, and this is my casing, what are the major issues in any cement evaluation or cement condition that we have in our reservoir? First one is this one right here. We call this one channel. Channel is a void, doesn't have any cement in it. So this channel is really a big issue, especially what this channel actually has. It probably later on will contain some gases, to contain water. It will really affect the condition of my cement. Okay, so this is a very important thing to find out. Do we really have this channel or not? The second one, that I don't have any bond between the cement and the casing. This area is empty. There is no cement in this area. So in this case, there is not really any bonding between the cement and the casing. It's very bad. Also, it may not have any bonding between the cement and the formation. So it's either between the cement and the casing, or between the cement and the formation. It's also a big issue. Or there's actually no bonding at all. So it's an empty zone, that there is no bonding with the casing, and there is no bonding on the formation. So the whole thing is missing completely any type of cementing. Or there are some gases, actually, we call it gas cut. The gas cut that actually bubbles here in the casing. So these are the major issues that we all like to avoid, and make sure that our cement, it doesn't have any one of these problems. Because all these problems in our evaluation, it affects the well integrity. And that's really a big issue. It's a safety concern that none of us would like for our wells to have any one of these issues. Okay. So now, if I really need to look at this in some more details, let's just take it one step at a time, one by one. Here is a situation where I have the cement is in a very good condition. I put the cement here. It's actually in good contact with the casing, and is good contact with the formation. Okay? So this is one case that we all like to have. Our cement, I'm looking also at the half of the wellbore, the other half should be the same. Right? I'm just putting here one half. Don't say that I'm cementing only one half and the other half is not. I'm just taking this as an example to look at the half of the wellbore. So the cement here is between the casing and the formation. Now, this we call excellent cement job. Okay, the bonding is good. The cement is filling the space or the annulus, and this is an excellent job in this case. No trouble here. This is what we all like to have in every well that we have. But well, life is not that easy all the time. In many situations, we see something like this. We see a gap here between the casing and the cement. This is one of the bad things that we see, that the casing here, we call it free. It doesn't really have any bonding with the cement at all. But there is a good bonding between the cement and the formation. Okay, so we have an issue here. They call it this bad cement job. This is not a good cement job. Okay, and we like to find out, do we really have this issue in our well or not? How can we find this issue? Okay. Second is, what are the possible troubles that may happen here? Let me give you some scenarios. First scenario, let's assume that this is a producing zone. This is your reservoir. And you made a big mistake here and you did not really do a good semen job in your reservoir. In front of the reservoir, what you will do, okay? Now, if you go and you did a perforation and you started producing, so your perforation is here, one of the perforations that you have, and you started producing from here. When the fluids come in, it will actually go through that channel. So this channel that you can see right there, or this bad semen jar that you see right here, it will be filled with your hydrocarbon, or it's actually gas, it will be really a big issue. So you start filling here, if it's water or gas or oil, whatever it is, filling the gap here, it's really bad. Okay, so it builds, pressure will start building up and your well will be in a condition that it may result in a really a disaster and unsafe act may happen during the production. So from the leak from the reservoir into between the casing and the cement may really find or result in a very, very bad health and safety issue and well integrity issue. So if the zone or part of the zone is perforated, that would be creating a very bad issue. So if the reservoir is gas, when there'll be a really big issue that we all like to avoid. So water corrosion may happen and also the integrity of the well bore will be in question. So this is a really bad thing that we don't want to have. Okay, now the question is, if it's not really a producing zone, is it okay then? No. So if somebody will say, well, I'm not gonna perforate this zone anyway, it's away from my reservoir. Am I in a good shape or I'm still in danger? Well, you're still in danger. The reason is, through the time, probably the casing will get eroded or pitting. Pitting means that some holes will start actually created inside your casing. So let's assume that the pitting happened and you start creating a hole here, okay, in your casing. What will happen is when your fluid is coming in, part of it will go through the hole and fill the spacing. So in this case, regardless, if this is a reservoir zone or this is not a reservoir zone, if it's not a reservoir zone, the problem may delay a little bit, but it's still in danger. Okay. If it's a reservoir, it's in danger almost from day one. Okay. So in both ways, if it is in the reservoir or not in the reservoir, it's really a good idea to find this out and do some remedy for it. So this one is not acceptable by all means, and we need to find out if our cement is really good condition or not. So similar situation will happen even if the zone is not in front of your reservoir. Second is another bad semen job. You can see the bonding is good between the casing and the cement, but the bonding is bad between the casing and the formation. Similarly, similar issue here, all possible troubles. It will be a trouble all the time. Fluids will get in. The condition of the cement will deteriorate. It will go back into the well bore and affects the well bore. So the same issues will happen. So it is regardless if it is between the casing and the cement and formation, anything in the cement is really a big issue, and we all like to avoid this from happening. So pressure will build up, the well will be under really bad condition, and disaster and unsafe things that may happen in the well bore. So now one of the things that we like to see is to detect this. How can we detect this issue? The most common tool that we all use after cementing, we call it Cbl, or Semen Bond Log. Semen Bond Log is a very important log that we do after we do the cementing. This is very critical to understand the situation and see how the bonding between the cement and casing and formation exists. So what we do here, let's assume that we have a case like this, the first case, where I don't have a bonding between the casing and the cement. Okay? Now, what we do is to put a sonic source, a source that emits acoustic waves, sonic wave, okay? Normal sonic wave, not really ultra or anything, just a normal sonic wave with normal frequency, okay? I don't want to go through into the details of the frequency and how we design, but just give you the idea how it works. So we'll actually create a tool that has a sonic source. Now, when the sonic actually emits, or the sonic source emits acoustic waves, the acoustic wave will go spread all around. Again, when I take one direction, that doesn't mean only one single acoustic will happen. The acoustic will actually be spread out. But just take an example here of one acoustic wave that came out of the source and started to be incident on the casing. What are the possible cases for this acoustic wave to take place? First of all, we learn in secondary school, probably, or probably in prep school, we learn that there are many situations that can happen. The first one, that this acoustic wave will reflect from the casing. So the casing will actually give us a reflection of the acoustic wave. So this is one thing, that the acoustic wave will reflect. Or the acoustic wave will go parallel. Okay, it depends on what we call incident angle. If the incident angle reaches what we call critical angle will result in the wave will be parallel to the surface of the casing. So it's either, if it's less than the critical angle, it will reflect. If it's equal to the critical angle, it will go parallel. If it's more than the critical angle, it will refract. So we call this reflection, we call this parallel. Sometimes we call it stony. And then the other one, we call it refraction. So we have reflection, we have stony, and we have refraction. It depends on the incident angle. So these are the all possible situations that you have. So actually you take advantage of this and we start measuring what's reflected from the casing. So we're measuring what's reflected, because this is the one I can measure. Well, I cannot put anything in here, or I cannot put anything parallel on the casing. So anything that reflects will give us some information of what's really happening there. Okay. So what do we expect in the case of no cement at all, or in the case of there are cement? So if there is a cement between the casing and the cement, that the bonding exists, okay, what will be the reflection? And if the bonding doesn't exist, what will be the reflection? That's why we call it Semen bond, the link, the connectivity between the casing and the cement. Okay, so they have actually multiple situations. So we put a receiver here. This receiver receives the reflected acoustic waves. We found that the distance between the sonic source and that receiver to optimize and get really good responses is it's about 3 feet. So between the source of the sonic and the receiver, it's about 3 feet. Okay, we'll show you some logging data where to see that the 3 feet is. So we have the distance, first distance between the sonic source and the receiver, it's about 3 feet. Okay, so in this case, the expectation of arrival time, if there is, then it will reflect from that surface to the wellbore again, and we receive it in the sonic receiver. The arrival time here is from 200 to 400 microseconds. It depends on the situation, depends on how bad the bond is, it depends on the casing type, depends on the distances, depends on the borehole size. So it will actually vary between 200 to 400 microseconds. So the expectation that I will receive the first reflection from the casing and the Semen bond between about 200 to 400 microseconds. Okay, this is one thing. So this is the time arrival time. Second is, what is the energy of the reflected one? So we look at two things. We look at the arrival time and the energy of the reflected one. Energy of the reflected one is very important as well. So in this case, we say, well, the amplitude. Every sonic wave or every wave is made, the energy of the wave is measured by the amplitude of the wave. The wave has two things. Wave has frequency and amplitude. Okay. So the amplitude or angle and amplitude, phase and amplitude. From the phase is the angle and the amplitude is the energy. So if you need to know the energy of the wave, you need to look at the amplitude of the wave. Okay. So we actually, in this type of tools, we record two things: arrival time and energy, which in physics or in measurement, we call it amplitude. So the arrival time and the amplitude reflects where it's coming from. If it's between 200 to 400 microseconds, it comes from the casing and actually looks at the energy that you will see. First of all, if there is no bonding here, this means that the wave will come in It will not find anything to attenuate with. It will not find it is actually a gap here. So there is no reason for the energy to be lost. There is the sonic wave is not going to give its energy to anything. There is nothing here for the sonic wave to give energy to. So the reflected one will have very close to the energy of the one that you sent. So there is no reduction of energy. So when we see there is no Semen in here, okay, the energy of the reflected wave will be very close to the energy of the source itself. The energy loss will be very, very, very small. So if the reflected energy, okay, that comes at a time from 200 to 400 is very close to the energy that you send from your source, then that's an indication there is no bonding between the casing and the semen. That's bad news. Okay, so the expectation if this is happening, that no grains to oscillate, so there is no reason for the energy to get lost. Okay, minimum loss of energy. Okay, which we call it minimum change in amplitude. So if there is a minimum loss of energy, the amplitude is not going to change because the amplitude reflects the energy. So if there is minimum loss of energy, then it's minimum loss of amplitude. Okay? So that this actually will tell us, do we have bond or we don't? So if the arrival time is from between 200 and 400, and I didn't find any change in the amplitude or the energy, then there is no bonding. So I know there is no semen in here. But on the other hand, if the bonding is good, then when you send a wave, it will actually see grains here, the semen grains. It will oscillate these grains. That's how the wave actually, how the propagation of acoustic wave happen. It actually oscillates the grain in their position. So when it oscillates the grain moves. The movement of the grain requires energy. Where the grain will get this energy from? From the wave. So it takes a lot of energy from the wave. That's why if there is cement here, a lot of energy will be taken out of the wave. This means that the amplitude of the reflected one will becomes very low. So why it becomes very low? Because it gave energy to the grains. It gave energy to the semen to oscillate. Yeah. So the oscillation of the semen grains will be as on the account of the energy of the sonic wave. So the expectation is oscillate the semen grains, then high loss of energy, because the oscillation of the semen grains will require energy, and it will get its energy from the sonic wave. Then in this case, the maximum change in amplitude. So we now know the basics, how we find out there is bonding or there is no bonding by using an acoustic wave. Okay. Here is an example. The first one here, you look at this, called TT3. Okay, TT stands for travel time. So travel time 3, what is this 3? 3 means this is the data coming from the 3 feet spacing. So the 3 feet spacing is actually accounted for the bonding between the casing and the semen. So that arrives it arrives at certain time, 200 to 400. If you look at the scale here from 200 to 1200, let me blow out this scale a little bit. Here's the scale from 200 to 400. I'm sorry, 200 to 1200 divided into 10. Then each one of these equals to 100. So this 200, 300, 400. So this is the area 200 to 400. So the area 200 to 400, you can see the arrival times in the area 200 to 400, which is our expectation. So area 200, 400. So we know this arrival time coming from the first thing, which is the casing and the semen. Now we need to look at the amplitude. Here's also amplitude 3. This is the amplitude of the acoustic wave for the 3 feet spacing between the source and the receiver. Okay. So this actually tell us, do we have high or low arrival? And it's actually counted from 0 to 100. From 0 to 100%. What is the percent of reduction in amplitude and percent of arrival in the amplitude? So this also called amplitude 3. Let me blow this out a little bit. Amplitude 3 measured in millivolt. This is from 0 to 100%. Then actually they scale it for you. So you can see the rate of the loss of energy or no loss of energy. So what is the loss of energy that you get from your acoustic wave? That will actually tell you the condition of your semen. Now, if I take this and try to evaluate what's really happening here, right? Something happened here again, I know. Here is the value that we look at here. Here is the value. Now, here is our amplitude. For example, this is high amplitude, as you can see right here. This is low amplitude. What a high amplitude means? It means that we did not lose much of energy. That's why the cement volume is very low. So if this is your cement condition or the coverage condition, what did you cover for the bonding between the cement and the casing? Very small cement volume is actually around there. So this upper zone doesn't have cement, doesn't have bonding between the formation and, I'm sorry, between the cement and the casing. Now, starting from this point, you can see good cement, and you can see some zones doesn't have cement, but in general, it's not a bad job because you still have very good cement between the formation and between the casing and the cement. So the value of the amplitude, first of all, you need to look at the arrival time, make sure that the arrival time from 200 to 400. Then you look at the amplitude. And if you have high amplitude, that's bad news. If you have low amplitude, that's good news. Okay. If we take another example from what's in the textbooks, if you read the case whole textbooks, you see this is the total arrival time. Now we are in the early arrival time, 200 to 400. So this is coming between the casing and the cement. Here is the Semen bond. Amplitude increases in that direction. So the amplitude here is high. So I have high amplitude here. Bad news. If you have high amplitude, that's bad news. It's really a bad job. How do service companies, Halliburton, Schlumberger, Baker, whoever do the case hole logging, how they present this data? They present this data, as I said here, the arrival. So they present this data in what we call variable density log, VDL. So this is called the VDL, or variable density log. What is it? Actually, they present the best semen job as straight lines. So there is no attenuation. Straight lines mean there is no attenuation. Things are straight, no attenuation, which this detect or represents bad semen job. So when you see this, what we call VDL, or variable density log, that's the reflection of the amplitude. So the amplitude here, and there is a reason for the dark and the white, why this is black and white, black and white. There's a reason for this. I don't want to go for that in this lecture, but you can see it's a straight line. When you see straight lines actually coming from the VDL, that's a very bad thing. So this is really a bad semen job, okay? All right, because you have high amplitude. This is what we call free pipe. It's really very bad semen bond. Now, here is another situation where you can see here is the cement amplitude, very low amplitude. Amplitude is increasing that way. So this is very low amplitude. That's good news. So how do you present it? It's not going to be a straight line. Huh? It's going to be something really attenuating. And that's the VGL actually comes in this line with a high attenuation. And you can see here, it's not really a straight line. Things started to attenuate. When you see this attenuation, it's actually a representation of change in amplitude. So the change in amplitude reflects that you lost energy. When you lost energy, means you have grains that took the energy from you to attenuate. So that's how we look at good job, bad job. So when you see straight lines, that's bad news. When you see really a change in amplitude, this is really good news, and this is a good semen bond job. Okay, so this is how we presented. If you are really a good engineer, then you look at the data. You look at the arrival time, you look at the amplitude, and make sure you understand probably even the percent. Okay, this is just a visualization for the normal casual user. Normal casual user, look at this thing, but actually you need to go to the data and see the percent of change. How this represents, because it can be actually an attenuation, but it's not really a high attenuation. It's a minimum attenuation, maximum attenuation, in medium attenuation. Arrival time, is it really in the good arrival time, or is it something really bigger than just the problem of the attenuation? So it's nice to look at this VDL, but if you are really a good engineer, you don't only rely on the VDL, you need to go and understand what you really see there and see if there is a semen bond or there is no semen bond, okay? All right. Now, we actually looked at the zone between the casing and the cement. Now, between the cement and the formation, let's go back to our source again. One more time, see what will happen in this area. Well, when we put this before, we looked at the first arrival, okay, at the 3 feet, and we understood that between 200 to 400, that arrival will come from the case. Then this one continued to go inside, okay, the one that refracted, okay, and went inside. There is now a gap between the cement and the formation. That gap now, there is a change here between medium. So what will happen here, again, one more time, when this one get incident on that zone, so this acoustic wave which actually penetrated the cement and went inside, when it sees here a change in medium between the cement and the formation, again, what happened here, it will happen there. So part of it will go parallel, okay? It will go into between these two zones. The other part will actually get reflected here and then get parallel again in the one which is stony and gets actually inside. So the situation was, if it reflected, it will reflect back into the cement to the casing. Then it will either go straight line, which is stony, or actually get refracted into the borehole again. So it will take longer time. So the one that will reflect from this zone, it will take longer time than the one that reflects from the zone between the casing and the cement. So this one will happen in shorter time, and this bonding will come to you into the formation in a longer time and also longer spacing. So what we found is you put another sonic receiver. So this tool, which is called the Cbl tool, the Cbl tool has a sonic source and two receivers. One of them at 3 feet that will actually count things coming between the cement and the casing. So this is the first arrival. The second one will come between the second bonding between the cement and the formation. That's why you need to receive it at a little bit further and at a longer distance. The distance that we put the second receiver here is 5 feet. So this one has two receivers. One at 3 feet and one at 5 feet. The one at 3 feet would actually receive data coming between the casing and the cement. The one at the 5 feet will receive data coming between the cement and the formation. Okay. Similarly, what is the expected time? Expected time for the first one arrival, remember, it was 200 to 400 microseconds. The second arrival between 400 to 800 microseconds. It comes later, it comes in a longer time. So it goes from 400 to 800 microseconds. And it follows the same rule, attenuation rule, amplitude. The amplitude is strong or the amplitude is weak. Yeah. So the channel, if there is a channel here and there is no bonding, so what will happen? No grains to oscillate. Follow the same rules: minimum loss of energy and minimum change in amplitude. And if there is no channel and you have a good bonding, then it oscillates the grains and loses energy and it loses amplitude. It's similar to what happened there. The only difference is it will come late and it will be received at a later or a longer distance from the sonic source. Okay. Is this the case here? Yes. Remember, we looked at the TT3 and amplitude 3. Here is the TT5, travel time 5. So the travel time 5, which is the one that comes at 5 feet spacing. So the 3 here goes for the 3 feet spacing, and the 5 will go for the 5 feet spacing. And again, the amplitude here, also from 0 to 100%, taking into consideration the change in the cement. Okay, so this is actually the TT5, and this is the amplitude 5, similar to what we talked about before in the TT3 and the amplitude 3. Here is also the TT5 coming from where? Coming from a longer time now. It's not 200 to 400, it's from 400 to 800. Here's the 400 right here. It's above 400. Remember, this is 200 to 1200. So it's 200, 300, 400. So it's above 400 to 800. It's higher than 400. So all this green part is higher than 400. It's coming from the bonding of the formation. Okay, and as you can see here, it also has higher amplitude here. So even the bonding between the cement and the formation is bad. So we found that the bonding between the cement and the casing is bad. Also, the bonding between the cement and the formation is bad, and better bonding between the formation and the cement in the lower section. So the upper section is really, really bad from both sides, from the casing and the formation. Lower section is in much better shape than the upper section of the casing. Okay, so that's how we look at the bonding between the cement and the casing. So this is a very bad bonding here, and the other one is a better one. With this, actually, we see that the Cbl tool is a good tool in finding out this bonding, but it actually has some drawbacks. Okay, the drawback of the Cbl, then when I tell you there is not really a bonding between the casing and the cement, you have no control, and you cannot visualize in the 360 degrees around the well bore. You cannot visualize that. What the Cbl give you is one piece of information, but the distribution of the cement around the well bore, the Cbl will not be capable of doing this for you. It's not going to give you this information. It gives you good bond, bad bond. But what is the good bond? It's happening at 0 degree, happening at 180 degree, in between, more than 180. What is the distribution of the cement around the circumference of my well bore? That tool is not capable of doing this. Okay? So the Cbl is a good tool. We usually use this. It's a tool that's routinely run in any well bore, and it's a good tool. It did what it should do, but it actually has some drawbacks. So the first drawback is the circumference coverage. It doesn't give us the circumference coverage in the casing, in the cement evaluation. So no information of how the cement is distributed across the circumference of the well bore. Okay, so in this case, yeah, it's a bad job, but well, you and I can guess what is a bad job. Somebody can say, okay, probably the bonding is bad in that direction of the well bore. Well, somebody will disagree. So no, it will not be that way. Nobody can prove that you are wrong, or nobody can prove that you are right. Okay, it's the way you're looking at things. Probably if the will is deviated or something, it will lean to some direction over the other. But it's again still a guess. It's your guess is like my guess. It's nobody can confirm that this is the reality. Yeah. So we don't have good information about the distribution across the well bore conference. In fact, this well, when they ran it, they found that here is the shape of the channel. Okay, this is how the bad job was. Okay, you can see it if you look at from 0 to 360. So it's actually taking a helical shape. Okay, it's a helical shape. It's not really a straight line, one direction that did not have the cement, or the other direction that had the cement. From where did we get this picture? That's what we will discuss in few minutes. Okay. So the circumference coverage is not really provided by the Cbl tool. Huge disadvantage and leads to improper evaluation. So what is the solution? Well, solution is to design another tool where the tool can actually look at the 360 degrees. So we have to have a 360 degrees tool. So Cbl is not going to give you this. We need another tool that can look at 360 degrees. Okay. So now what we do, you use a rotating head. Now there is a tool that has a rotating head. The rotating head will rotate, and it will send acoustic wave across the rotation, okay, while it's rotating. So it will cover the 360 degrees, and it will actually detect the arrival at these different angles. So that's what this is a solution for. You use a rotating head. The other thing is, in this tool, we used a very high frequency sonic. Why we use a very high frequency sonic? Because actually what you are interested in is the distance between the casing and the formation. This is the distance that you put the cement in. So why do you need low frequency and go deeper into the formation? Low frequency means that the wavelength is very high. And wavelength is very high means you go deeper and read deeper into the formation. I don't want to read deeper into the formation. Frankly, I want to see only the zone between the casing and the formation. So there is no need to use low frequency acoustics. So high frequency acoustic will actually limit the zone I will be interested in this zone only, the zone between the casing and the formation. I need to look at the Semen. Okay, so there's no need to use low frequency. That's why we use ultra high frequency. Okay, the ultrasonic means the frequency is very high, so the wavelength is very small. When the wavelength is very small, I can cover only the zone of interest, which is the zone that has the Semen in. Okay, so the ultrasonic is the one that we use, very high frequency source to consider or to consider only the zone that has the Semen, and there's no need to go deeper into the formation. Okay, so high frequency means low travel distance to only examine the Semen and to limit other effects. Okay, how does it work? Look at this. For example, if this is my well bore, I can divide my well bore into segments. This is my rotating head. The rotating head will have an acoustic wave here, and then the rotating head will rotate. So I can divide the segments and measure the acoustic wave in every one of these segments. So I can tell you segment 1, segment 2, segment 3, every one of these has a certain range of angle. So if it's 360 degrees, for example, if we divide it by 16 or probably 18, then that one will have 20 degrees. If it is 18, a little bit higher than 20 if it is 16. So you look at the rotation here, for example. If you allow this head to rotate, then you will send the wave across this rotation, and then you actually go for bin and the amplitude. So you record the bin number 1, bin number 2, bin number 3, and then you get the amplitude values. For if this goes for bin number 10, then you record the data at bin number 9 or 10. Then if it goes here, and you continue recording here, because every arrival arrives at a certain bin, then you record the arrival at every certain bin. Then you can actually draw an image of what's really happening across the world. So this one does not provide one value. It looks at the image across the 360 degrees, okay? Without going into some details, it's the same phenomena, but with multiple or more deliverables than only a single measurement. So because it actually limits the zone of interest with using the ultrasonic, so it doesn't go deeper into the formation. So it can give you very good information of the casing and good information of the Semen. So it actually concerns itself into the casing and into the Semen. Okay. So in the casing, it will give you, for example, the minimum internal radius. So now radius of the casing. So it will actually measure the radius of the casing. Now, if you have corrosion in the casing, this one will detect that, because if the corrosion took place, the casing inside diameter will increase. So it will measure the casing inside diameter. Okay, so in this case, you will know if you have corrosion inside the casing. Now, it will also give you the diameter of the casing outside. So outside the casing, so the internal diameter and external diameter. So if you get to the internal diameter, that's controlled by the frequency of the arrival. So the internal diameter will be measured, the external diameter will be measured. So if you have corrosion on the external, it will let you know that. If you have corrosion inside the casing, it will let you know that. If you have scaling inside the casing, probably you can also find this out. And then if you subtract both, you will get the thickness. So you can get actually the erosion of the casing. So it will give you very, very good information for thickness minus the average. Here is now the thickness of the casing minus the average. Average means the manufactured average thickness of casing. Then you can see if there's any corrosion or not. If it's positive or negative. Positive means there is a corrosion there taken out, or some scaling actually up there. Cement is the same way, but it uses something called impedance. I'm not going to talk about the impedance too much, but let me give you just an idea what is the impedance. Impedance actually is a function of the density of the material, okay, and the travel time of the acoustic wave. So the travel time of the acoustic wave plus the density of material, we actually call it, or we can come up with the impedance in this case, okay? So without going into details about the impedance, you need to know that it relies on the impedance to find out what's the situation there. And that's because the impedance is a function of density. Okay, as I told you, the impedance is density a combination of density and travel time or travel velocity. So in this case, if it is a function of density, then I can tell you if there is gases in there or not, liquid there or not, if there are gases inside the cement or not, liquid or solid. So they actually give you this in different colors. The red one is gas, the blue one is solid, is liquid, and the dark one is solid. So you know that there is liquid here because it is blue. Liquid here means it's not really a cement. Okay, there is no solids. So this one has a very, very bad cement on the top and good cement at the bottom. So bad cement here because it's liquid and there is not really a cement there. There's just some liquid in here. And you can see there, it's solid. That's why if you look at it here, this one has seal or no seal. So the blue one is no seal. So there is no cement in here. It's not sealed. The casing is not sealed. But at the bottom, we know it is a seal because we can see solid of cement, and that there is no seal of cement here. Okay. So this tool is much, much, much better than the Cbl in finding the actual cases. What's the inner diameter of the casing? What's the outer diameter of the casing? What's the erosion that happened in the casing? In the cement, it will give you an image of the 360 degrees. You can look at the direction of the channel if there's any. Also, it looks at is there any gases, any liquid, any solids. So if there is gases in your cement, it will point this out. If you're the bubble of gases that you have, or if there's any liquid, like there is not really much of a cement in the zone, it will show you this. Also show you the distances or the differences between a zone that is liquid filled or zone that is cement filled. So it's really a good tool that can give you a full coverage and much more information than the Semen Bond. So this part covers the casing and the cement that we've been concerned of. Okay. All right. So now to go to the third part, which is the saturation behind casing. So we actually looked at in the previous lecture, we looked at what's inside the wellbore. In this lecture, we started talking about what's happening between the casing and the cement. And we found that we can cover this with two different ways, either with one single reading that we call it Cbl, or with a coverage 360-degree readings with the ultrasonic tools that actually look at the coverage that gives you information on the casing and information on the cement. Okay. Now we need to know what's really happening in our formation now. So we need to go to the third zone. Third zone is saturation behind casing. How much water saturation do I have now, currently now? And how much hydrocarbon do I have currently left now? Okay. So we call it behind casing formation evaluation. So behind casing formation evaluation, tell us what is the situation now, especially if your reservoir now, you started producing reservoir and your reservoir pressure went down under the bubble point. So what do you expect? I can see some gases in there. Okay. Do I have gases there or not? What is the saturation of gas and what's the saturation of oil? Okay. What's the saturation of water? Now, if I go and inject some, say, water injection, the first recovery that we have, so I have water injection or tertiary recovery, did some gas injection or whatever. So what is it? Okay, what is the situation that I have now in my reservoir? Yeah. Right. So we call it where what is really required now from the tool that we use to find this out. Okay. Is it the same requirement from the tool that we used in open hole, or the case tool has relaxed a little bit the conditions for the saturation behind? If you remember, in the open hole environment, it's just to give you a cartoon here of what's really happening in the open hole environment to compare and see, do we really have the same issue that we had before in the open hole or not? Remember when you start drilling the well and then we started going there with the drilling fluid? What do you do with the drilling fluid? Drilling fluid has a certain mud weight, which is slightly higher than the formation pressure. Okay, so the mud weight that we have, it will provide pressure in the wellbore that's slightly higher than the pressure in the formation. Why? We need to prevent any leak from the formation into the wellbore. That's unsafe. Okay, so in this case, we slightly go higher than the pressure of the formation. If you go slightly higher than the pressure of the formation, then well, invasion will take place. Some of the filtrate of the mud will get into your formation. So that's going to happen. We have extra delta P between the borehole and the formation. So the invasion will take place. So in this case, you will see something happening. That very nice formation doesn't exist anymore. You'll see multiple zones started to exist. The first one we call it flush zone. Second one we call it invaded zone. Third one is the uninvaded zone. So we have actually three zones. Flush zone is completely flushed by the mud filtrate that got invaded, and a zone that has a mix between your original fluids and your filtrate, and then a zone that is not affected. How far deep can I get? It depends on the delta P. So actually, you look at delta P versus radius of invasion. Here is my delta P, the difference between the mud weight and the pore pressure here, or pressure in the well bore and pressure in the formation. That delta P will actually create invasion, and the invasion will stop when delta P is so weak where it doesn't invade anymore. Okay, so the radius of invasion can be calculated from that. So this means now if I need to measure in the open hole, I need to measure my fluid saturation and need to get away from the flush zone because that doesn't represent my reservoir. I need to get away from the invaded zone that doesn't represent my reservoir. I need to get the uninvaded zone. That's the one that represents my reservoir. So my tool in the open hole has to read very deep. So remember, we read deep resistivity. So that's why we read deep resistivity. We need to get away from the flush zone, away from the invaded zone, and we read deep into the formation. Okay, so that's the requirement in the open hole. So in the open hole, the requirement is when you go and do logging for the open hole, your resistivity has to be deep enough to get away from the invaded zone to give you the proper value of the reservoir condition and the reservoir fluid. Yeah. So for this one, that this is the resistivity tool that you have, has to be deep enough to get this, and we use this resistivity tool to actually come up with the evaluation of the formation fluids, the percent of the hydrocarbon, percent of water that you have there. So that's under the condition that this resistivity tool reads deep enough in the formation that can actually detect the change of the fluids. Yeah. Is the same situation actually in the cased hole? Well, let's just understand that. Well, once the drilling is stopped, and you started putting the casing in, and you started doing the cement that we just a few minutes ago we looked at the condition of it. Then you perforated, okay? So you perforated the zone. Then you started producing it. When you start producing, what will happen here? Everything comes from deeper into, and it gets very close until it produced here in the perforation. So the flushing that happened before in the open hole is no more existing. So there is not really any type of fluid, flushing fluids or filtrate, because it's already gone with the production. So this means I don't have invasion in my cased hole situation. There is no invasion anymore. That invasion or the invaded zone, what we talked about before, vanished, gone, doesn't exist anymore because we started producing our reservoir. So in this case, do I really need, in the cased hole, do I really need a tool that reads deep? No. There is no need for the tool to read deep. All that the tool needs to do is to get beyond the casing and the cement. That's it. If the tool can actually go beyond the casing and the cement and goes shallow enough, it doesn't matter. Okay, if it gets some depth, a good depth, that's good enough. But it's not really a requirement because I'm not scared of any change in the reservoir fluid saturation because there is no invasion. Okay, so that actually relaxed more into the how we measure the saturation behind pipes. So the only requirement for any tool that actually give us information on the saturation behind the cased hole, because that's why we call it behind pipes. So the saturation behind pipes is at the production pipes, the casing pipes, or whatever. So the saturation behind pipes doesn't require very high depth of investigation. It actually goes, if anything that goes beyond casing and cement, for a little bit of 1-2 inches inside the formation, that's good enough. So in this case, we'll be in good shape because there is no invasion to get me worried about the fluid saturation. Okay. So cased hole resistivity. Now the question is, well, can I actually have a cased hole resistivity? Because that's what you actually do in the open hole. In the open hole, we measure the saturation with the resistivity tool. Will actually, can I do measurement in the cased hole with resistivity? You will be actually facing a problem. Let me show you, well, does this really fit the environment? Here is our situation. Here is our casing. Here is our semen, and here is our formation. Now, if I need to measure resistivity, I will have two resistivities. One is the formation resistivity, okay, with the semen, and also the second is the casing, because casing is a metal. This is a metal, okay, a metal and a non-metallic component. The metallic component is the casing. The non-metallic component is the semen and the formation. So the R of the formation here, and also is parallel with an R casing. These two, formation resistivity is high because it contains rock, it contains hydrocarbon, resistivity is high. Casing resistivity is very, very low. It's a metal. Metal resistivity is very low. Now they are connected in parallel. Now if I put any current, okay, what you expect from the simple circuit analysis? Well, this is very low resistivity. It will take the most of the current. I can say, assume I'm taking 99% of the current in the casing, and only 1% will go into the formation. Then your measurement will be in question, because you didn't put enough current here to really make sure that you believe that your measurement is correct. So in this case, I'm in a dilemma. I cannot do this. Okay, it's be very difficult to do. Okay, when I say I cannot do, but well, with the advances in technology, we can actually measure very low voltage, and that was Schlumberger did in one of its tools. Okay, so the idea, it's a challenge. Is it doable or not? Yes, it is doable. Okay, there's a Schlumberger cased hole formation tester. Sorry, cased hole formation resistivity. So cased hole formation resistivity is a tool developed by Schlumberger, and actually this one based on the very small current that we can detect from the formation, even if the casing exists. Okay. So to reduce the casing effect, so we normally actually have the ability to measure very, very low voltage. This is one thing, and also to have either a stationary measurement. You stay there for quite some time to really gather good information, or to repeat the measurement. So whenever we have a measurement that's very low, okay, that's what we really do, even in the lab. You repeat the measurement more than once, okay? And you try to stay there as long as you can to really give enough time to build a good signal to noise ratio, okay? So in this case, it puts some limitations on the tool for the speed, limitation on the tool. Sometimes you need to run it stationary. So it puts some limitations on the tool, but it's doable. It's actually doable. So you do multiple measurements and get the statistical variation. How can you apply this rule here? We'll do measurement stationary or at very low logging speed. So you can find your way if you are really in bad need to do a resistivity. Resistivity, if you can measure the resistivity behind casing, believe it or not, that will be a superior measurement if the measurement is in good shape, because the interpretation of the measurement is very simple. Okay, it's not as complicated as other methods that we will discuss also here. Okay, so it's good. So the principle of what the cased hole formation resistivity is all about is to use a source at the surface. So the current source will be at the surface, not in the bottom, not in the tool. It will be at the surface, and you send very low frequency. Remember, when we need for the wavelengths to read a very short distance, you increase the frequency. If you need the wave to measure a very long distance, you decrease the frequency. So we actually lower the frequency. Here, we use a very low frequency source. It actually sends all this voltage across the different layers. So we send a very low current very low frequency current that goes inside the formation between the layers. Okay, so this is the first thing, very low frequency alternating current that goes inside your formation. Then you try to measure the potential difference, the voltage between 2 points. Okay, so between this point and that point, I can get you the voltage. Okay, so in this case, you can actually measure the voltage in a nanovolt. So you have to have very high accurate measurement of voltage that can measure up down to nano. Nano is 10 to the negative 9 of a volt. Remember, it's a casing, so the casing will take everything from you, and you will end up with a very small measurement that you need to measure, which is the nanovolt. So your measurement here or electronics has to be very sensitive, very accurate, all the way to go to reach into the negative 9 of a volt. So it is a challenging technology, but it's available. Okay. So in this case, and sometimes you have to repeat the measurements. Sometimes you have to calibrate the casing. So it requires more things to get really a good resistance. So as you can see here, it's a challenge. It's a challenge to measure the resistivity behind the casing. Big challenge, because you have a very good conductor inside the well bore, which is your case. Okay. Is it done? Yes, there is an example here, comparison between open hole and cased hole resistivity, and you can see it's actually good agreement. Okay. Well, if we really can do this, then you will save us a lot of effort in the evaluation. Why? You can go for Mr. R sheet, a very simple R sheet, for example, and I can get a very quick current water saturation in my reservoir using the cased hole resistivity. For example, I just write RC in open hole and write RC in cased hole. Write RC water saturation in open hole, then I can use RW open hole, phi, and R resistivity RT open hole. Okay. Also, in the cased hole, I will write it in RW cased hole, in R, and also R cased hole. Then I can divide these two over each other. The porosity will cancel out, so I don't really need to know porosity anymore. A will cancel out. Okay. Then the SW cased hole over SW open hole, the ratio that changes between from open hole to cased hole is just the R open hole over R cased hole if there is no water injection on anything. Because if there is no water injection, then the R open hole, RW open hole is the same RW cased hole. So in this case, they also will cancel out. But if you actually have water injection and you started changing the water inside your formation, okay, so in this case, you have to keep R open hole different than R cased hole, and then you can get the ratio this way. Still, very straightforward way of interpreting the water saturation currently compared to what the water saturation was in the original well when we drilled this well in the open hole condition. But as you can see here, it's a very challenging approach, very challenging measurement. That's why we don't really rely heavily on this. So we need a different method. We need a different methodology, not affected by casing or semen. So casing affected our measurement in the resistivity. It took all of our current, left us with a very small current going through the formation. Now we need something that's not really very much affected by casing or semen. Okay, and better accuracy. So in this case, we can get a better accuracy in this case. Back to Mr. Neutron. Mr. Neutron will come in and solve the issue. Mr. Neutron is helping us a lot in formation evaluation, guys, as you know. In open hole, in cased hole, Mr. Neutron is there all the time. Okay, I always call it Mr. Neutron. So Mr. Neutron comes in, hey, I'm the solution for it. Okay. How come, Mr. Neutron? How can you help us in this? Let's just go back and look at the atom. What is the atom? The atom is mainly a nucleus and electrons going around the nucleus, okay, in orbits. Okay, this is the simple description of an atomic structure. So this means that the electrons are rotating around the nucleus. Electrons are charged particles. Any charged particle that moves, it generates an electric field. So the electrons will create the first an electric field. Also, every electron, it looks like guys, if you think about it, like the solar system that we live in. Things are rotating in orbits, and they rotate around itself. For example, Earth rotates around the sun, and it rotates around itself. It's exactly what happens to the electrons. Electrons actually rotate around the nucleus, and they rotate around itself. So when they rotate around themselves, they create a magnetic field. So the rotation around themselves on the axis, around their own axis, it creates a magnetic field. So they actually, and there is an electric field there and magnetic field there. That's why when we hear the electromagnetic field happen, so there is an electromagnetic field surrounding the nucleus. So if there is any charged particle, it will be very difficult to get in. If any charged particle, it will be very difficult to get in because the atom is protected by its own shield of electromagnetic field. It requires more energy to get into this. But Mr. Neutron is not. Mr. Neutron is not a charged particle. So it will not be affected heavily by the electromagnetic field. So in this case, if I bring a neutron source here, and the neutron source will emit neutrons, neutrons will get in easier than anything else because they are not charged particles. So the effect of the electromagnetic field around the neutrons is not going to happen. So Mr. Neutron can go and all the way and interact with the nucleus without very high effort compared to anything it's a charged particle or so. So Mr. Neutron is always helpful because it can travel inside the formation and it can take its own trip in there. So let's just follow Mr. Neutron and see what's really going to happen to him. If I have a source that will emit a very high neutron energy, okay, we measure the neutron energy in mega electron volt. Again, I'm not going to go through the what is the mega electron volt. You can actually read about it, but it's a very high energy anyway. It's a mega energy, it's very high energy for the neutron. So the neutron is emitted by very high energy. I'm going to talk about very high energy. It's even higher energy than the normal neutron too. Okay, so it's about 14 mega electron volt, and it's man-made neutron source. So in this case, you can control the energy. So 14 mega electron volt is the energy that you have from the source. Okay? So the source actually you will emit very high energy neutron. So very high energy thing when it goes, it hits the atoms. Okay, it hits the atom. What will happen? Any collision will be loss of energy. Okay, who's gonna lose the energy? Mr. Neutron. Mr. Neutron will lose energy, give energy to the nucleus. So the nucleus will get excited. It will get more energy than it requires. So the nucleus will get excited. When the neutron gets excited, will go back to stable state by emitting what we call inelastic gamma ray. Okay, so the inelastic gamma ray comes out as a result of a collision of very high energy neutron with the nucleus. So when a very high energy neutron comes to the nucleus, it will lose energy, give this energy to the nucleus. The nucleus will get excited, go to the higher state, then it needs to go back to its lower state, stable state. So it will emit the excessive energy in the form of gamma ray. So the gamma ray that it has an inelastic energy gamma ray. But Mr. Neutron just keeps going. Yes, it lost some energy, but it can still keep going. When it keeps going, it'll go to what we call elastic scattering. So it actually keeps losing energy, and so on, until sometimes it will lose enough energy, okay, until it reaches a very, very low energy. So it keeps losing energy across the collisions with the nucleus of different atoms in the formation until its energy becomes very, very low, much lower than the 14. Okay, to the level not mega electron volt, to the level of a fraction of an electron volt, not even in the meg. Here is about 14 meg. No, it will lose energy until it was even a fraction of the electron volt, one single electron volt, which is what we call 0.025 electron volt. This is what we call thermal energy. So the thermal energy, once the neutron comes down to this energy, 0.025 electron volt, not mega electron volt. Now it's very, very low energy. Then it actually, you should put it in your mind that somebody was really running with a very high speed until he lost his breath. He cannot do it anymore. He will slow down. Okay, when he slows down, he can easily get captured. It's exactly like we normally do in our day life. Yeah, you start running at the beginning with all of your energy still there. keep running until you probably do 2 miles or whatever, then your energy will go slower down, down, down until you cannot even walk anymore. Okay, so if you cannot even walk anymore, if for God forbid anybody wants to hurt you, it will hurt. They will hurt you. Okay, why? Because you have no power anymore. This is exactly what happened to Mr. Neutron. When it goes and does all of this scattering, it will lose its energy, get really tired. Energy is lost all of the energy. Now it's a very, very low energy. So it gets easy captured by any element. So the elements will capture Mr. Neutron, and they will generate what they call captured gamma ray. Okay, they will generate what's called captured gamma ray. So we have two gamma rays actually, inelastic at the beginning and capture at the end. But the difference is that in the inelastic, the neutron is still alive. In the capture, the neutron is gone. It's captured. Captured means it's gone. Means somebody took it. Okay, or some element took it. I'm going to say somebody. Some element took it. So that element who took it actually create, instead of the neutron, it will create a capture gamma ray. So it will give us a gamma ray. Okay, we call it capture gamma ray. Okay. All right, capture gamma ray comes out, and Mr. Neutron is gone, dead. That's it. That's the end of Mr. Neutron here in this case. Right? Who actually do this? What are the elements that can do that? Well, here is the capture element. Look at this. Chlorine has a very good capture of the neutron. Hydrogen has good capture of the neutron, but carbon does it. Chlorine and hydrogen are in our water, correct? Carbon is in our hydrocarbon. So this means the capture will be heavily affected by water and less affected by hydrocarbon. So let's use this idea of capture to identify the water and calculate the water saturation. So that's exactly the basic idea behind it. Okay, let's just use this to really find out the water and then identify the saturation of the water. So chlorine lives in water, hydrogen lives in water, both actually provide capture. We use this to identify that. So let's just design a tool in this case. Tool is very simple. I will go for a neutron source, high energy, and will allow the neutron to come out and make the collisions with all these elements. Then all these elements until the neutron energy goes very, very, very low, it will generate a gamma ray. Then I will collect the gamma ray. Then I will use two detectors, near gamma ray detector, far gamma ray. It's not a neutron detector, it's a gamma ray detector, because I need to detect the capture gamma. So near gamma ray capture and far gamma ray capture. From these two, I can actually find out what to call the capture, okay? The measurement of the captured neutron, which we call it sigma total. So sigma denotes or reflects the capture ability of a formation with all the components of the formation. So sigma T or sigma total is the total capture ability of the formation of Mr. Neutron, okay? So how we calculate water saturation from capture of sigma? I say, okay, here is the sigma total, the total capture in a formation. Some of them will get from the rock, some of them will get from the clay, some of them will get from the water, some of them will get from the oil. Okay, true. So sigma total components, so the rock will absorb neutrons, the clay will absorb neutrons, water will absorb neutrons, oil will absorb neutrons. Which one is the strongest? The strongest is water. So water will be the most dominant in all. Okay. So in this case, sigma total will be sigma rock, volume of rock, sigma clay, volume of clay, sigma water, porosity times S water, which is the volume of water. Sigma oil, volume of oil is porosity times 1 minus S depth. So as you can see, this equation is a strong function of S depth. Okay, and this is an exact equation, by the way. There is no approximation whatsoever. So SW here can be calculated from this equation. How can I get the sigma total? That's what the tool will measure. Total sigma, total absorption. How can I get the volume of rock, the volume of clay, the porosity? I can get that from the open hole. It's not going to change between open hole and cased hole. The limestone volume or sandstone volume or whatever, it's there. Clay volume is not going to change. Porosity is not going to change. The only thing that changes in the cased hole is the fluid. Okay, all right. So then How can I get the sigma rock? Well, it is tabulated. Limestone sigma is known, sandstone sigma is known, dolomite sigma is known, so we know that. Okay. How about the clay? Well, we can. How about the sigma water? Well, sigma water is a function of how much chlorine do you have. So if you tell me what is the salinity of your water, I can tell you what the sigma water is. Very straightforward, because it's a function of chlorine, and we knew previously that chlorine has a good absorption of the neutrons. So sigma water is a function of how much salinity or how much chlorine do you have in your water. Sigma oil, well, it's very well known. So sigma oil is known, sigma gas is known. So we know everything. Clay, you can get that from the logs. So all the components are known. The only one that's not known is the SW that we can calculate from this equation. Okay? So here's an example where you can see here, this is the open hole data. I have actually neutron and density, and I have the PE. PE here is shown 5, indicating that the upper zone is limestone, showing less than 5 in the lower section. So if you look at this, this is the limestone section. Also went down here went here to 5 again. Then also another limestone section. Actually went down here to 2, which actually telling me this is a sandstone section, and also went down here to 2, telling me that this is the sandstone section. So this is a reservoir that has mainly limestone and 2 sands at the bottom here. Okay. So now we look at this and we calculated from this. We calculated the neutron density here, and you look at the sandstone and the limestone. Then we calculated the water saturation and the hydrocarbon saturation. So this is the original hydrocarbon saturation in the reservoir. Very nice zone at the top here was really high hydrocarbon saturation in there. Okay, so that actually at the original time, at the time of the open hole data, before we produce anything. In this well, and after 2 years, they started monitoring what's happening now. Do we have the same situation with a very nice hydrocarbon there? No, we started to produce for 2 years. So what is the current hydrocarbon saturation and water saturation? So they use the sigma. Okay, they measure the sigma value. Here is the sigma value across the reservoir, and they use this sigma to calculate what is the current hydrocarbon saturation and water saturation. Okay, so sigma analysis, as we said, we have 2 zones. We have a limestone section and we have a sandstone section. We know the limestone volume, we know the clay volume, we know the porosity here for the limestone and for the sandstone. So we can fill out all these from the open hole. The limestone volume or sandstone volume, the clay volume, the porosity. We know all of this from the open hole data. The sigma of limestone, as I said, limestone is very well known. Sigma is 12. Sigma sandstone is 8. It's very well known. It's tabulated. Okay. Sigma oil is 22. Sigma oil is 22. So sigma oil in the same reservoir is the same, and it's 22. It's also tabulated. Okay. Water salinity is 123 kppm in this feed. 123 kppm. So actually, I go from the relationship. I know the salinity percent, I can get you the sigma. It's very well known in any of the cased hole logging tools. Now, if I know the salinity, here is my 123 kppm, then my sigma is 63. So I know if you tell me the salinity of your water, easily I can find the sigma, the sigma of the water. Then the sigma of the water is 63, and the sigma of the water is 63. Okay, where is the sigma clay? Okay, sigma clay here is 32, and sigma, I know that from the clay or from the logs. So everything is known. The only thing that's not known or unknown is SW. So I can actually go and calculate SW for the limestone section and for the sandstone section. When we did this, here is the current situation now. It used to be originally full of hydrocarbon. Now it's not. Water started to fringe in. So here is the water. You can see this zone is no longer 100% oil. No, it's not. It's probably lost about 50% or so. Okay. So this is the current distribution. Look at this zone, for example, that used to be full of hydrocarbon. No, it doesn't exist anymore. If you look at this zone, for example, used to be full of hydrocarbon. No, it's not anymore. This zone is not anymore. So there is a big change between the open hole current the open hole situation of hydrocarbon and the current situation of hydrocarbon. So the Sigma tool actually give us the ability to look at the current situation of water saturation and hydrocarbon saturation, so you can actually find out the situation of our field on a monitoring basis, based on how long between the monitoring, every 6 months or every year, I can actually look and find out what is the situation of my reservoir. Okay. So any other method? Yes, one more method that's called the carbon oxygen. This is actually beyond, it's based on the inelastic gamma ray, and it's beyond the scope of this course. Okay, to go and talk about the inelastic, it will take me more than a day to really explain how the carbon oxygen works. So I will stop at this point. Carbon oxygen is really beyond the scope of undergraduate, so it should be for the graduate courses. So carbon oxygen is not going to be covered in this webinar. Thank you very much. I hope that you guys enjoyed the journey on the cased hole logging as an introduction, so you get some good understanding of the cased hole logging. I know we don't teach this in undergrad, but it's really good to know some basics of the cased hole logging. Thank you very much, and I'm ready for any question and answer. Mariam, please.
Thank you, Doctor, for this informative session. We actually have some questions from the audience. So the first question is that, what is the importance of the casing collar located in the CBL?
Well, the casing collar is something that we use for the casing, and it's actually casing collar is a metal, so it will be detected easily by the CBL. It will be there for any acoustic reflection, so you can find out the casing collar very clearly there. So we don't actually get good responses behind the casing collar because of the multiple iron components in there. So you will see an indication of casing collar, but you know, the situation of the semen behind the casing collar will be something that you know, not going to be able to see it 100%. Okay.
Okay, thank you. The next question is that, how can we mitigate the problem of bad cement if it occurs between the cement and the formation?
No, that's a big challenge. That's a big challenge. You need to worry about this, and you need to always monitor it. In the between the casing and the cement, yes, we can handle this. Sometimes we can go and do some, you know, treatment of this type of channels. If it goes beyond that, that's really a big issue. I need to make sure that you monitor this very carefully, and probably it will also control the way you produce this well. And you need really to make sure that this issue will not lead to any unsafe situation in the field. So you need to monitor that very carefully. Yes. So designing a good semen job, guys. Calculating the proper volume of cement, and you don't just do a very quick calculation, because I saw this in many cases, quite frankly. People do a very quick calculation of semen volume. They assume so many things. They don't rely heavily on caliper to really calculate the actual semen volume required. They do very quick calculation of semen volume, and they don't pay much attention to the bad semen jobs, and that can lead to really a big issue in the future. Yeah. So calculating the semen volume is very important. Making sure the return when you do, I don't want to go into the operation and how we do that, but you know, you need to calculate the semen volume, and you need to look at the return of the casing that's coming at the surface when you do the casing semen job. So many things in the operational that you need to take care of. Make sure that you're really having good semen job, or you know, things can happen, and unsafe acts in the field can happen, and probably can lead to, you know, not just journey, some people injured, but it can go to death and fatality, which is, God forbid, that can happen. Okay.
Okay, thank you. How can we calculate the water saturation in cased hole if the reservoir is a gas reservoir?
Well, it's the same. The actually gas reservoir is even easier. Okay, because there are actually situations in the cased hole logging, especially when you use the sigma as we talked about here. Sigma has a limitation on how salty the water should be. Okay, because fresh water and oil, they have very close sigma value, absorption value. Okay, so it's about 22 to 23, whatever. Uh, Gas, no, gas has a much lower sigma. Gas has about 6 to 7, 8 sigma. So even if you have very low salinity water, like say 25 to 30 or whatever, which is may not be working very well with the sigma, but in case you have gases, then you can easily get the water, the gas saturation. So either gas or oil. In the case of oil, make sure that your water salinity is high. In the case of gas, don't even worry about it. It will work both ways. Okay, so it's either salt water or even fresh water. It will work very well. For gas, it will work very well. Doesn't require any condition on salinity. For oil, it will require conditions on salinity. Yeah.
Thank you, Doctor, for answering the questions. Now, as a reminder, this session has been recorded and it will be uploaded soon on Biopetra's YouTube channel. Now, I hope you enjoyed the session. Thank you, Doctor, so much for your time and effort. And now I hope you have a nice rest of the day and see you next week. Thank you.
Thank you very much. Bye-bye.